alternative in this section you'll be presented with is finding that equation from a graph, but it'll be extremely similar. For example, this first one, you can see that it is odd in power based on its shape. It's most likely, again, not most likely, it will have a negative coefficient because of its shape. And it looks, I mean, it's odd, so it's 3, 5, 7, it just depends on the zeros. But there's a 0 here at -1, and then if you'll notice, here at +1, it bounces, so there's a double 0 at +1. The other point that you're given is down here at -1, and that's going to be the point 0, -1. It's giving you the y-intercept. That'll help us come up with our constant. So if we plug what we have in, we have a constant, we have a 0 at -1, so I'll do x plus 1, and then I have a double 0 at +1, so I'll do x minus 1 squared. And then I'll use my point, plug in for x's and y's, get -1, it's a constant, times 0 plus 1 times 0 minus 1 squared. So that leaves me with -1 squared is 1, constant is -1. So the possible function here, I'll do f of x, since it's on the graph, is negative x plus 1 times x minus 1 quantity squared. That's for that problem. The next one, if you'll notice, has 1, 2, 3, 4 crossings, but because of its end behavior, it's an odd-powered polynomial, and because of its long-run behavior of positive infinity as x goes to infinity, and negative infinity as x goes to negative infinity, it's going to have a positive coefficient. So that's what we need to find for A. And I have 4 zeros, but I need it to be an odd power, so I need 5 zeros really. If you'll notice here at 1, it's a double because it bounces. So if we start with our function, which I'll call h of x because it's in the graph, I'll just start here on the left side. I've got a constant 0 at -2, so I'll do x plus 2, 0 at -1, so I'll do x plus 1, a double 0 at +1, so I'll do x minus 1 squared, and then another 0 here at 3, so I'll do x minus 3. Okay, the other thing that's given to you in this graph is this point, and that point is 2, -1, and that's just an xy point that we're going to use to end up finding our constant, which we hope is positive because of the shape of the graph. So I'll plug -1 in for the function value, 2 in for all the x's, 2 plus 2, 2 plus 1, 2 minus 1 squared, 2 minus 3. Clean that up, we get 4 times 3 times 1 times -1. That becomes -12, and the constant is positive 1/12, which is what we needed it to be, was positive. So our function is 1/12 times x plus 2 times x plus 1 times x minus 1 squared times x minus 3, and you are most welcome to leave it factored in that form. All right, here is another odd-powered polynomial, but I want you to note what's in this picture, and it says note the appearance at the origin. Because right now I see 3 zeros, but a lot of times, you know, double roots tend, or double zeros, will bounce off of the x-axis, but a triple zero will sort of level out sort of flat at wherever the 0 is. And that's what's happening here at 0. This leveling out that happens is actually going to be a triple root, and we'll count that 0 3 times. So we do have 1, 2, 3, 4, 5 zeros. It's just one of them is going to be a triple root. Let me get rid of this. So, and you also have 0, 0 as the y-intercept, so that'll be a helpful point whenever we come up with this. So f of x is, oh, and the coefficient is going to be positive just based on the fact of the end behavior going like it does for the long run. So we have a constant. I'll start here on the left. A 0 of -1 makes x plus 1. The 0 at 0, you can do x plus 0 or x minus 0 if you want, but it'll be 3 of them. And then the 0 here at 2 will become x minus 2. And then if I use my point of 0, 0, because that's the only other point that was given for this function, I'll plug 0 in for the function value, 0 in for all of the x's, and get, it looks like I'm probably going to get 0. One, 0, -2, yeah. Which did not work out at all. I'm going to have to revisit that one. Don't know if you can tell that that's a point. So we'll do that one in another example. Let's look at this one. We have an even-powered polynomial. We have the end behavior pointing down, so it's going to be a negative coefficient. I have a 0 at 2, a 0 at 3, and a bounce at -2. So that's going to be a double root or double 0. And then I have this nice indicated point at -1, -3. So our function will be some constant times x plus 2 squared, because the double 0 factor where it bounced, x minus 2 and x minus 3. I'll use my point, plug in a -3 for the function, -1 for the x. Clean that up, you get 1 squared times -3 times -4. So that becomes 12. And you get that the constant is -1/4, which is what we needed it to be, negative. So our function is -1/4 times x plus 2 squared times x minus 2 times x minus 3. Possible function here. All right, another 4th degree, or even degree, not necessarily 4th, but even degree, with a positive coefficient because of the end behavior pointing up. We have a 0 at -2. We have a bounce at -1, so that'll be a double 0. And then we have a y-intercept given as 0, -2, and then we have another crossing 0 at 1. So our function, which in this case is h of x, is a constant with x plus 2 times x plus 1 squared times x minus 1. So then to find the constant, plug -2 in for the function, 0 in for all the x's, and you get 2 times 1 times -1. So that's -2. Constant ends up being 1 here. So our function is just the x plus 2 times x plus 1 squared times x minus 1. Coefficient, constant of 1, you don't really write the 1 there. So here's your final answer for that one. Okay. Here's one with a fraction point. So so I thought I would work on this one. It's another even degree with a positive leading coefficient, again because of the end behavior in the long run. I've got a 0 at -1, so that'll be x plus 1. A crossing at 0, which is a 0 of 0, so it's just a single x. Or again, if you need to put x minus 0 or x plus 0, you can, but it's still just an x. And then I have a bounce at 1. So that bouncing is going to be a double 0 at 1, so x minus 1 squared. And then we'll use our point, x equals -1/2, y equals -27/16, to come up with our constant. So -1/2 plus 1 times -1/2 times -1/2 minus 1 squared. And again, that's just a crossing here, a single 0. It didn't do any flattening out, so we don't count it more than once. So what that looks like is 1/2 times -1/2 times -3/2 squared. And multiplying all of that together, you get -9/16. And then to get rid of that, you do -16/9. 16's cancel, negative is a positive, 27/9 is 3. Constant turns out to a nice 3. And the function that's possible for this graph is 3 times x plus 1 times x minus 1 squared. And just to note, you'll probably see this written as 3x and then the x plus 1 and the x minus 1 squared. They're technically the same, but a lot of times if there's a single x, it'll get written out front with the coefficient for final notation. That should work. All right, last one. Another even degreed polynomial with a positive leading term for the coefficient, just based, again, on end behavior. We have a y-intercept at 4, and we have 2 bounces. So we have a double 0 at -4, and another double 0 at +3. So when I go to write the function, I do x plus 4 squared and x minus 3 squared. Again, whatever the 0 is, you change the sign in the factored form. Then I'll use my point, 0, 4, put 4 in for the function, 0 in for x. I get that that's 16 times 9. Which is 144. Simplify that, I get that my constant is 1/36. Again, leave it, don't give a decimal. So your final function for f of x is 1/36 times x plus 4 squared times x minus 3 squared. And you can leave it just like that.